This example is referring to a spanning tree with degree constraint. So as you might have seen in the example of a spanning tree, we defined some virtual demand for each node, and then try to find out how we can create a graph, which is a tree, a connected one, but without any kind of loop. So now we want to find out more characteristics of the graph and enforce some additional constraints. So if you look at this graph, which is a tree, we can easily calculate the degree of each node. For example, the degree of node 6 is 1 because it has only one edge connected to it. Degree of node 1 is 2, it has 2 edges connected to this node. And the degree of node 9 is 3, and so on and so on. Okay, so maybe in some cases we want to limit the degree of each node. So in order to do so, we have to limit the number of edges that can be connected to a graph, to each node. So we can write down for each I, we can write down such equation or constraint: UIC plus UCI should be less than n degree, and the summation should be done over all the C except I. So we add this constraint to the formulation and see the results. So you can see here, if I limit the degree of each node to, for example, 2, then the same connection, the same dots are connected to each other in a different way. So here you can see that the maximum degree is 2. But how should I write it down? Let me show you the Python code. Okay, so here you can see the Python code. Initially I import every required package, and then I define the required variables. So the variables are the same as the example minimum spanning tree, and but we have to add a new parameter called maximum degree. So a max degree is a parameter, it's a mutable parameter, and you can specify a default value for it or not. And also the variables are exactly the same. Then I create some random locations for those dots and calculate the distance between each pair of them. Okay. Then there are some constraints for this model, and as we discussed before in the previous example, each node should follow the balance rule. So how much we have generated is equal to how much we are consuming or exporting. So here only for node 1 we have a production or generation, and at each node we have some amount of demand, let's say I divided by model.n, or you can specify something else or a constant number or whatever you want, and then how much exporting, how much importing from the other nodes to do the summation, and this constraint will create the balance rule. And then the other constraint is telling us that if node is connected to each other, if two nodes are connected to each other, then a flow can exist between those two nodes. And this one is telling us the maximum degree of each node, how should it be specified. Okay, so model UIC plus model UCI and summation over C, but for some specific C's, not all the C's. If I is different with C, because we are not connected to each other, to ourselves, and it should be less than model degree. And the objective function is the same as before, U multiplied by D, summation over all I and C. So here, let me give you a point here. So here you can see that if we write down this the code in this way, what will happen? It will put the R and C for every possible combination of R and C, R in I and C in J. Okay. This way will also create some additional U when the R and C are also equal to each other. So to avoid that situation, I add an extra kind of specification here. So here, if R and C are exactly equal to each other, then so if R and C are not equal to each other, then this summation should take place. Otherwise, it will create some situation that U R and R, for example, you know, U1 and 1, U2 and 2. So to avoid that, we have to add this extra constraint. Okay. Let's. I should write down if. Okay. So this will finish the definition of the constraints, and we choose the solver as the GLPK, and we can specify the n and max degree. So let's run the code with each other. So I've run the first tab. Okay, it is run successfully, and also the second tab is done. Okay, and the third tab is specifying n equal to 10 and max degree is 4. So it takes time to finish the solve statement, because for example, if you have 10 nodes, then 10 multiplied by 9 is telling you how many binary variables. It will be 90 and binary variables. 2 to the power 90 will be the number of combination that you might have. Okay, so and finally I run this. You can get this graph, you can see here. Okay, so initially as you can see here, the degree of the nodes is, the maximum degree is 3. For example, here is 3, here is 3, but if you add that constraint and consider that, then it means that a new tree will be created, and you can see it here. So I run the final tab for you. You can do it as well. So so this way it has to recalculate how they should be connected to each other. So you can see here that the same location of the nodes, but different way of connecting them together. Okay, thank you very much.